Hello, everybody. If you missed class today, we are starting a new unit, which is about mathematical modeling. I thought that I would start by asking people, like, what does that phrase mean to them? And we uncovered a lot of other meanings for the idea of modeling. So when we're talking about modeling, we're not talking about three-dimensional modeling, like making character models or CAD models. And we're also not talking about modeling that you might do in a high school class or even a college class where you're making physical things to represent scientific concepts. So this is like a cell model made out of clay. Those are not the idea of modeling that we're talking about. You might have heard of climate models. The class was not too certain what climate models were for or what they actually are. They thought maybe climate models are about predicting the weather. Climate models can predict a lot of things, but one of the major things that we're interested in is predicting global average temperature. And what a mathematical model is it's a set of equations that describe what influences the thing that we want to predict so that we can make more accurate predictions. So this picture is not super on point for the words here, but it was the best picture I could find on short notice. Things that contribute to the temperature are these scientific concepts here, and the scientific concepts are governed by equations, and so you can kind of put equations together to make predictions. In epidemiology, which is the study of communicable disease, there's a really famous model, the SIR model, where S stands for susceptible, I stands for infectious, and R stands for sometimes recovered or removed. And the idea is you can use a set of mathematical equations to make predictions about infection rates and death rates in a population when there's a communicable disease. So the SIR model was one that was used, a lot when COVID happened and other epidemics before that, and undoubtedly in future epidemics. So the math here, this is calculus, so you don't know this math. But that's the idea of what a mathematical model does. You're predicting something, and the model itself is a set of equations that describe what's influencing the thing that we're trying to predict. So for our class, we started with something like a little less weighty. This is kind of a silly question, but it's one that illustrates a lot of issues that come up when you have to do modeling. So in class, I ran it this way. I said I'm going to ask them a question, and they have 30 seconds to write down their gut feeling, and then a little bit more time to improve their estimate based on calculations. So here was the question. I found this YouTube video where someone filled their house with these kind of funhouse balls. I have a whole bunch of these balls in the classroom, actually. And so the question was, in our actual classroom, if we wanted to fill it up all the way to the top, here there's some extra space, but if we wanted to fill in every nook and cranny with funhouse balls, how many balls would it take? So if you want to play along, you can do this. So write down your gut feeling, order of magnitude. Is it like 1,000, 10,000, 100,000, million, 10 million, 100 million, billion? Where is it? People in the class guessed all kinds of stuff. It was a huge range. And then they used a QR code to make their predictions. If you were going to make some better estimates, you might want some questions answered, like what are the dimensions of the room, or what's the size of the ball? I had them do things like estimate the length and the width and the height of the room. I told them the diameter of the ball. For these notes, let's just have you jump to our kind of final conclusion. So this was our note-taking form, where I have a little blurb about how I think about mathematical modeling. Some key ideas in modeling are that you have to make simplifying assumptions, and there are sometimes parameters in your model which you can estimate the values of or determine experimentally. And usually when we're modeling, you can kind of loosely think about three broad steps: deciding what we want to calculate or predict, and then thinking about what influences that thing, and then writing equations for how all of our variables are related to each other. So for this particular problem, most people thought about a very, very simple model. So here was the simple model. They did something like this. They said that the number of balls to fill the space should be the volume of the room divided by the volume of a ball. And that's a very, very simple model. Of course, we're not just going to look at the room and think, oh, this room is 5,000 cubic feet. you can't just guess at the volume of the room. So their simple model actually had equations for each piece here, but it's useful to think about it conceptually this way. So for the volume of the room, people did width times length times height. For the volume of a ball, some people treated the ball as if it was actually a cube. So I said that the ball was 2¼ inches in diameter. So they just treated the volume of a ball as if they had a cube that was 2¼ inches along a side. Some people looked up the equation for a sphere. So the equation for a sphere is 4/3 pi times the radius cubed. The radius, of course, is the diameter divided by 2. So this is still our simple model, and if I just showed you this, you might think, well, gosh, that's a lot of letters. But it's a very simple idea, just volume of the room divided by volume of a ball. Okay, so the thing to know about simple models is even this idea, or rather, this idea involves a lot of assumptions about the room that aren't true. So here's some assumptions. Our room is not actually a rectangular prism. It's not shaped. It's not shaped like this. So our room actually has a little triangular ceiling section that looks like this, if I can draw it properly. So assumption 1 is our room isn't shaped this way. Another assumption is, here I'm looking at the entire volume of the inside of the room, but there's a lot of stuff in the room that's taking up some of that volume. There's furniture and things. So another assumption is this assumes an empty room. A third assumption is if I'm dividing the entire volume of the room by the volume of one sphere, that assumes that when I fill the room with spheres, all the volume of the room is being taken up by spheres. But if you imagine, well, you don't have to imagine, let's look at the picture. So that slide that I had before, here, you see that there's a lot of empty space in between the spheres. You know, the spheres don't pack perfectly tightly. So it's just not true that all of the volume in the room is being used up by spheres. There's some empty space that doesn't get used. So it's pretty normal to have lots of simplifying assumptions whenever you model. The assumptions could include ignoring things, like ignoring furniture. It could include simplifying things, like assuming that the balls are actually shaped like perfect spheres that are all the exact same size, or assuming that the room really is like a perfect rectangular prism and doesn't have, like curved corners or other things in it. So that's all quite normal. Let's go ahead and try and figure out how we could incorporate, make a more sophisticated model by incorporating things in our equation that might take account of these other things. So here's our improved model. I had the class brainstorm some ways that you might modify the equation to account for furniture, or to account for the fact that there actually is space between the spheres. So here's what we came up with. So let's start with the same thing. We've got the thing we're trying to calculate, the number of balls. And let's have volume of room. And then people said if you could estimate the volume of all the furniture in the room, you could just subtract that volume. Because the leftover volume is the amount that is available to be filled with spheres. So volume of room minus volume of furniture. How do we find the volume of the furniture? There was a great discussion in 7th block. Somebody decided that, if you had a couple of days and a budget, you could do things like fill a large bathtub with water and submerge one of the desks and measure the difference in volume between when you had no desk in it and then when you submerged the desk. And that difference must be the volume of the desk. And then once you know the volume of the desk, you can multiply by how many desks we have. Same thing for chairs. You could estimate in other ways. But I think the important thing is once we have an estimate for the volume of the furniture, let's just remove that volume from the available volume to be filled up with balls. We can still keep volume of ball down here. That's fine. But how do we take account of the idea that there's space in between the spheres? So if you imagine that, well, I mean, you could determine this. Let's see, how do I want to explain this? So imagine filling up some space with like a bunch of spheres. Not 100% of this volume is being filled up by spheres. Some of it's empty space. So you might ask, what percent of the overall volume is actually empty space? Or conversely, you could say, what percent of this volume is not empty? And that's the volume that gets filled up by spheres. So actually, if you appeal to Wikipedia, Wikipedia claims that if you randomly pack spheres, about 64% of the volume that you're packing into gets filled by spheres. So what you can do is on the outside here, you can multiply by that percent. Percent of volume used by spheres. Because if I'm not using my full volume for spheres, I don't want to divide my full volume by the volume of a sphere to find how many. Like, I only want to divide the volume that's actually full of spheres by the volume of a sphere to figure out how many. So this could be a term that's a percentage that would make my estimate more accurate. So what have we learned here? Let's backtrack. Oh, sorry, I should say for people who missed class and you're taking notes here, you probably do want to note down what's the simple model, what's the improved model. Make sure you can think clearly about how all these pieces work. And then notice that the simple model involves a lot of assumptions. The improved model also involves assumptions, like we have to estimate this value here. We're still assuming that the balls are spheres. We're still assuming they're all a constant diameter, things like that. But do make sure that you have something like this notated down. And then at the top of the page, go ahead and make these notes. So, this was kind of a silly example, but this idea that there are a lot of influences for the thing that we care about and that we have to ignore some of them or simplify others, that's going to be universal in modeling. We will always have to simplify reality and ignore some parts of reality that, actually influence what we care about. Because if you don't, then it's too complicated to predict anything. So definitely write this down. Lots of influences, we ignore and simplify. Another thing to write down is that the model involves lots of constants, sometimes called parameters, and that you have to measure or estimate the values of those parameters. And that if your model ends up making bad predictions, there's a couple reasons. It might be that the structure of your model is bad, but it might be that the structure of your model is just fine, and that some of the specific numbers that you gave as input to your model aren't accurate estimates. So for example, like, what if we just misestimated the width of the room? What if I was a little bit wrong about the volume of a ball? Like, that could really, or like about the diameter of the ball, rather. If there's slight measurement error about the diameter of the ball, my overall model could be great, but the overall calculation is going to be very, very different. So these are all general considerations when you're modeling. We ended by considering a couple of more real-life examples. So, modeling infectious disease, modeling climate. The mathematics for that are quite complicated. Calculating balls in a room is rather silly. But there's a middle ground with problems that are serious problems, but that involve math that we also actually know. So imagine safe maximum occupancy for a restaurant. Like you go to the restaurant and you see posted on the wall somewhere, maximum occupancy 350 people. So like, what's that about? We decided that was probably about the maximum number of people, not that will fit in the room. We're not trying to pack them in like spheres in a room. It's about how many people can safely exit in a short amount of time if there's an emergency, like a fire. So instead of so we're thinking about maximum occupancy, but what we're really interested in is something like we're really interested in something like, what's the maximum number of people that can exit the room in some fixed amount of time, like 1 minute or 3 minutes. So you can go through the same modeling process. You can think, okay, we know what we're trying to predict. how many people can exit the room in 3 minutes, what is going to be related to that? So things like the size of the room are important, but probably more important than that is going to be the number of exits, the size of the exits, probably the number and layout of the obstacles, if there are any clear paths, considerations like how quickly people move, particularly when there's a high density of people. So you could start rating these quantities down and then start thinking about what are the mathematical equations that say how they're related to each other. Different question. So this is a policy question. Should California eliminate speed limits on highways? Right? Famously, the Autobahn in Germany has no speed limit. People can drive however fast they want. Should we do that in California? Well, so you might think, yes, certainly we should. And you could give reasons that are based on values. You might say freedom is the most important value, and people should be free to drive however fast they want. And on the other side, people might say, well, a more important value is public safety. You only have control over how well you drive, but if there are other drivers that drive badly, you don't want to put yourself at risk just because other drivers drive badly. So, their freedom doesn't outweigh your right to safety. But these are all value questions. You could take a philosophy class and think about how you would have a debate about value questions. What I wanted to point out is that there are factual questions that you can make mathematical models for. The safety side of the argument is making an assumption that, probably a good assumption, that if you eliminate speed limits, people will drive faster, and that if people are driving faster, they'll probably have more accidents, or the accidents will be deadlier. Okay, but maybe it matters how much. Maybe if there's a lot more accidents and they're a lot more deadly, that would cause people to think differently than if it wasn't quite so much. So you could make mathematical models to try and help you predict, if you eliminated speed limits, how many more accidents per mile driven would there be? What's the probability that they would be more deadly? Last one for now is how long should a yellow light be? If yellow lights are too short, there are problems associated with that. If the yellow light's too long, there's problems associated with that. So, what's relevant to figuring out how long a yellow light should be? Probably stuff like the size of the intersection, the average driving speed for that road, maybe the density of traffic, maybe people's reaction times. There's a lot of stuff that might be relevant. And so, again, you would create mathematical models to help you answer questions like this. Okay, come back in the next video for a specific modeling problem that we kind of ended the class with. And it's still not, a super interesting one, but it'll be a good one to practice on.